little bit more than you guys do, only slightly more. Speaking of, where do volcanoes go when they need to pee? The lavatory.
Wow.
Yeah, that's the best one I got, folks. That is the best one. All right, let's talk about some volcanoes. Keep in mind, the entire Hawaiian island chain, every bit that you walked on, wouldn't have been there had it not been for a volcano, right? None of it was there, would be there otherwise. I mean, we can get into the detail about, well, the coral broke up, and this is true. And, the sand on the white, the sand beaches that aren't black, that sand, as we talked about maybe 6 days ago at this point, pooped out by fish, right? That's how that sand got there, broken up coral pieces. So this part is true. But the island itself, the reason that those islands are there are because of volcanoes. It is the recycling of material from within the earth that has come up, as on the surface, and starts to erode and enter the ocean again. It takes millions and millions of years. It's not a fast process, but it's a recycling of this material. Everything, as a reminder, everything is connected. Everything on this planet is connected. We don't get shipments of water or carbon or anything else from outer space. Whatever we have on the planet is what we've always had, and it's all we're ever going to have. These resources just move around from one form to another. Now, you remember this slide. I went over this before. This is just sort of to refresh your memory. Keep in mind, the place that we're living on this planet is very, very, very thin compared to the thickness of the planet as a whole, right? The mantle is insanely thick. It is a very thick layer. And within that, we have some very, very dense layers that are very, very warm, but they're solid because of the pressure. The part that we're floating on, the crust is floating on, is a liquid, red-hot layer of molten rock. And I showed this slide before, that we're living, obviously, on the continental crust, which is sitting on top of the oceanic crust. And this is all floating on this mantle. And you have to imagine it just like it's a boat, floating on a sea, just like we are right this second. It's exactly how it's oriented, because that rock is liquid underneath there. Now, I mentioned this before about how the Earth is very much set up. It reminds me of a hard-boiled egg. And I think it's because I really like hard-boiled eggs, and when I was a kid, Easter, coloring the eggs was one of my favorite things. When you break a hard-boiled egg, you get cracks all over the shell, and you can see the individual pieces, but those pieces don't necessarily just fall off. They're still connected like puzzle pieces within each other, right? The entirety of that egg is still covered, but you see that there is covered by individual pieces, and that's exactly how the crust of the Earth works. And we happen to be at the moment on the Pacific Plate. Now, how many people here live on the North American plate? Show of hands. Great, all right, that's most of us. How many people here live on the Pacific Plate? Yeah, those of us who live in Southern California, along the coast, we are Pacific Platers. And I imagine we have a bunch on the Australian plate as well. Yeah? All right. Yeah, so these things are moving. These plates are in motion. And I know that from my plate, the Pacific Plate, if I just hold out long enough, like 60 million years, I'll have oceanfront Alaskan property as this plate moves north and west. Where these plates bump into each other, though, this is where we have geologic activity. And I mentioned this before. It's very well known. You've heard of the Ring of Fire, right? Not the Johnny Cash song, but the actual, scientifically described Ring of Fire. This is places where these plate boundaries are causing geologic activity. We're going to talk about this. So here is...
Good morning, Splendor family. This announcement is for all remaining guests. All remaining guests who have not administered their self-test to kindly do so at this time and coordinate with your stateroom attendant. Thank you.
I'm going to hope that you guys already did your test. Good job. Way to do what you're supposed to do. I appreciate this. So anyway, back to this. So the ring of fire is, and I've colored this so you can see it a little bit better, basically follows the edge of that plate. And this makes sense because this is where the two plates are going to be rubbing up against each other, or three at this point. This is actually a lot of plates that are rubbing up against the Pacific plate, but this is sort of the shape of the Pacific plate. This is a slide that shows earthquakes magnitude 4.0 or greater since 1898. So you see the brightest orange, or brightest yellow, is in the same shape as the Pacific plate. And this makes sense. This is where the boundary of the plate is. But something that is unusual is what is happening right there. There's no plate boundary. What is that? That's Hawaii. That's just right where we came from. So, and that is seismically active. Why on earth is that possible? Like, it's not rubbing against another plate. We're going to talk about this. First, let's go through what these boundaries look like. So you have divergent plate boundaries. This is what it's like in the middle of the Atlantic Ocean. You've got plates that are pulling apart from each other. Well, what happens in the space in between? What goes there? Is it a void that just goes down to the center of the Earth? What do you guys think? This is where new Earth is being formed. This is what's driving these plates apart. So in the middle of the Atlantic, new Earth is being formed. These plates are moving away from each other. The opposite is a convergent plate boundary, where you got two plates that are headed towards each other. Inevitably, one plate will subduct under the other one. And when this happens, that plate gets really, really hot, it melts, and that material is recycled back into the Earth. Usually, pretty much always, it also creates volcanoes just on the other side of the plate that rises above. Because this, as it goes down, gets hot, it'll come back up. The other type of boundary that occurs between these plates are what's called a transform fault, or a transform plate boundary. This is what, if you live in Southern California, this is the San Andreas Fault. Where I'm from, this is our big fault. The big one we're always worried about is this. These transforms, they're sliding past each other. Now, they don't slide past each other smoothly. It's like pulling two pieces of Velcro apart. They kind of like grind and sort of move in a jaggedy fashion. There actually was some thought. I don't know how high up this actually went, but I was made aware of this. This is the actual conversation that occurred among geologists about, do you think there's a way that we could somehow lubricate our transform fault? Like, could we take a bunch of used McDonald's fry grease and just dump it in that valley, for a couple thousand miles, so that when it would move smoother and we'd have less earthquakes? And this was actually an idea that was kicked around. And one of the big sort of reasons that it wasn't considered, which all of it seems incredible, educated people were having this conversation, but the fear was that we don't know what would happen if we filled this transform fault with grease. Maybe it would move too fast. Like, instead of moving, just a little bit, all of a sudden, next earthquake, maybe we'd move a whole bunch. And we don't know, we don't want that to happen. We don't want to end up in Alaska tomorrow. We want to get there in 76 million years. And so this was one of the thoughts. They actually considered this. I will tell you, in transform faults, like where I live in Los Angeles, the county courthouse, which was built in the early part of the 1900s, it's moved 120 feet from where it was actually built, just because we're sliding north. And that's not a huge amount of distance, but that's evidence of what's happening there. We know that we're on a piece of land that is in motion, just like right now we're in a ship that is in motion. Even though, you can feel the rolling, but even though you don't feel like you're moving, we're traveling. This is something I wanted to talk about. I didn't go over this last time I brought this up. This idea about what happens with these different plates as they connect with the liquid red hot earth beneath it. So here you've got a boundary that's spreading open, right? Like I mentioned in the Atlantic Ocean. You've got new earth being formed, plates are heading apart from each other. Here you've got one that's subducting under the other. And what happens is this gets hot, volcanoes erupt. Not only that, the earth on the top part here gets bunched up as the plate that's subducting scrapes underneath that plate that's going to override it. It bunches up that plate. If you can imagine sort of two pieces of material of whatever, paper, whatever else, maybe not paper will slide easily, but think of something else, maybe felt, and one goes under the other, it's going to grab that one on top and kind of bunch it up. It's going to make it fold and ripple. And this is what happens. This is what's the cause of these coastal mountain ranges, where you've got two plates that are one subducting under the other. It causes this ridgeline, and this ridgeline is littered with volcanoes. So if you're from the west coast of the United States and Canada, you're familiar with the Cascade Mountains, for instance, right? You got Mount Rainier, Mount St. Helens, Mount Baker, you have all these volcanic ranges, and it's because the land right there has been crinkled up and now is volcanically erupting. But the thing that is weird is here, when you have this sort of thing happening, this isn't a plate boundary interaction. This is just a plate sitting on top of a hot spot, what we call a hot spot. And you got liquid hot rock coming up, breaking through the surface of the crust, making what we call shield volcanoes. It's, the question is how and why. What does this do? Well, this is how the Hawaiian Islands are formed. And I know we talked about this, but I'm going to go back over it a little bit again. So this is an image of how the Pacific Plate's moving. You see the plate boundaries. Hawaiian Islands, not near any of the boundaries, smack middle of the plate. But what's happening under the Hawaiian Islands, remember the Hawaiian Islands is a long chain of islands. Long chain. We've only occupied the most recent of the islands. But underneath the big island right now, that's where that hot spot is, where that liquid hot rock is coming to the surface and making the volcanoes, the active volcanoes. So you can see, we talk about Kauai and the older islands from millions of years ago. They're way past the hot spot, which is why they're extinct. Those volcanoes are extinct. But as you move closer to the hot spot and you get to the island of Hawaii and Lokini, the new one that hasn't broke the surface yet, these are active. That's why the active volcanoes are only on that island, because they're still close to the hot spot. If you were at Kilauea, if you went and visited these things, you're standing basically 60 miles above that hot spot, almost directly above that hot spot, directly above this boiling cauldron of red hot liquid rock. And 60 miles, it seems like a long ways when you think about it, but in terms of geologic space, that is not far at all. You are sitting right on top of it. It's crazy. When you think about this, and here's an image that I like to use, and maybe this will resonate with you, maybe it won't. Again, going back to hard-boiled eggs. When you boil water, put these eggs in, right? You put the eggs in there, you see the water boil, you see the little tiny currents that exist inside that stock pot full of boiling water. When you put your eggs in there, you see the eggs move in those currents. Even though the water is boiling, even though it's really, really hot, there are little tiny currents inside that pot, that confined space of boiling water. That's exactly what's happening in the mantle. It's exactly what's happening. That's what's creating this hot spot. It's basically like the part where the current in your pot of boiling water is coming to the surface and moving that egg. That's what's creating this hot spot. That's what's creating the Hawaiian Islands. So if you look at this, you see here's the chain of the Hawaiian Islands all the way up. Now keep in mind that most of these aren't islands anymore. They've been eroded away and they're below the sea level. But they go all the way up almost to the Aleutian Island chain, right where the Pacific Plate's running into the North American Plate. Something that's fascinating though, this red line, this red line represents about 30 degrees north latitude. Now why is this significant? About 30 degrees is where the water starts to significantly change temperature. Now I mentioned about the beginning of the coral reefs. I mentioned about how the coral reef basically originally attached to the island, right? The fresh lava starts getting coral that's attached to it, and as the island gets eroded, it kind of pulls away from that reef and you get a fringe reef around it, eventually becomes a barrier reef. Remember all this? So, and as that coral's growing, that reef stays intact because it's got new the coral animals are depositing new amounts of limestone on it, so that reef is maintaining its size and shape and growing, whereas the island can't get any bigger, it's shrinking. But at 30 degrees latitude, it starts becoming too cold for the corals. So now the corals die north of 32 degrees latitude, and the islands that have these coral reefs, these fringing reefs, all of a sudden that coral can't live anymore. So the erosion that's happening to the landmass also happens to the corals. This means that the entirety of the structure, the original lava that came up from those volcanoes and formed those islands, and the reef all start being eroded. And the whole thing basically just starts disappearing from existence. They sink below the surface of the earth, or below the surface of the water, and they basically start disappearing. Which is why when you move further north, these seamounts, what we call seamounts, are very, very deep compared to being just under the surface or at the surface, because they've been eroded away. It's the ocean reclaiming this material. Now, volcanoes are so special, so unique. We've created a bunch of national parks to cover these. We talked about Helikala being the world's largest dormant volcano, that it hasn't erupted in hundreds of years, and that it formed more than 75% of Maui. There is a theory that actually did more than that, it kind of split off, but we all agree at least 75% of that island was formed by this one volcano. If you had a chance to visit it, you could see that, it's a massive, massive, massive crater. That cauldron that it has was huge. 7,000 feet deep, 7.5 miles long, 2.5 miles wide. It's huge. You could put the entire island of Manhattan in it. The national park that we've created, the Hawaiian Volcanoes National Park in 1916, houses some of the volcano from the Big Island. Kilauea, which is one of the most active volcanoes on the planet, and I actually went up there and I didn't have, and I had mentioned this, the captain had me do a late night announcement as we were moving from one side of the island to the other, maybe you heard it, because I know some people said, hey, I went outside at 1:30 and I didn't see anything, and I felt bad having to make that announcement because I knew you weren't going to see anything, but when the captain asks you to do something, you do something. But I went to see this, and you could see steam. And in one section, it wasn't just steam. You could see some of the sulfur, some of the other chemicals that were underneath coming up. And I took a video, but I wasn't able to integrate it into this because I'm pretty stupid when it comes to computers. But you could see that this is still active, seismically, and in terms of the movement of this liquid rock, still active. It's massive. It's incredible. That particular crater, that is what's considered to be sort of the birthplace of, or the home of Pele, the Hawaiian goddess of volcanic activity, of creation. That's her home, that volcanic crater, and it's still active. Now, I talked about how we basically call volcanoes one of two things, either dormant or extinct or active. But we're talking about ones that aren't exploding currently. Dormant ones means they haven't had any activity in 200 years, right? So we think of them, it's not that they won't, it just means that they're dormant, they're asleep. They're still alive, they're just asleep. If you've been inactive since then, you're extinct, like an animal. It's never coming back, right? So the volcanoes in Maui, in Kauai, in Oahu, those are extinct. Those are never gonna become active again. Because why? They're nowhere near the hot spot. They got nothing feeding them. The active volcanoes on the Big Island that we visited, and hopefully you got a chance to go see some, are these three. So, Kohala, which is the oldest volcano on the island, is extinct, right? 60,000 years ago was about the last time we think it erupted. Mauna Kea, 3,600 years ago it erupted. So we're calling that one dormant. The other three have erupted most recently in the 1800s, in 1984 for Mauna Loa, and Kilauea in 1983. They've erupted so recently that we call them active. And then, of course, we have Little Lohi growing down here. This is about 15 miles off the coast and down about 3,000 feet from the surface. So we expect that it's going to take somewhere around 50,000 years for it to break the surface of the water and become its own island. At that point, it's hard to say whether it'll connect with the Hawaiian Islands, or with the Big Island of Hawaii, and sort of be an offshoot, or if it'll be its own standalone island. There's no way to know. And frankly, none of us will be here in 50,000 years. In fact, the entire planet may not be here. This is image of it exploding underwater, 3,000 feet below the surface. This is it venting out, same way that it will be happening above the surface. This is happening underwater. This volcanic activity doesn't care whether it's exposed to the air or if it's submerged in water. It's the same activity. This is sort of a rundown of how these things work, and I'll move through it now.
Good morning, Carnival Splendor family. This announcement is for all remaining guests. All remaining guests who have not administered the self-test at this time kindly coordinate with your stateroom attendant. All remaining guests at this time who have not administered the self-test kindly do so. Coordinate with your room attendant. Thank you.
Hello. Okay, back on. All right, so like I'm saying, here is the basic growth cycle of the island, the volcano which makes the island, right? So you've got these stages where they're below the surface of the water, right? They're growing. These are shield volcanoes, right? So they're growing slowly. They're not erupting massive explosions. And then eventually they break the surface. Now keep in mind, water has a lot to do with this. Water, especially like when you're 3,000 feet below the surface, water is applying a bit of pressure to you. That pressure is impacting the growth of the volcano. Volcanoes, the eruption and the rate at which they grow are all pressure related. Not just by the pressure of the water squeezing down, but mostly by the pressure of that liquid hot rock underneath it pushing up. And as you get closer to the surface, you get less of that pressure pushing down on you, so that the pressure underneath overwhelms it more. It tends to grow faster. When it hits the surface and it's got no water pressure binding it, now it becomes a lot more active. Now it grows a lot faster. And so as it grows, you get, what we talked about, it starts to erode. You start getting coral that's growing on the fringe. And eventually the erosion, and you may have a little side volcanic activity here, extend out, like we had in Hawaii, like we're having in the Big Island now. Eventually, though, it erodes away, and all that's left is that ring, that coral ring around it. And this is what I talked about as these islands are moving further north of 30 degrees latitude. You have very little island left. You've got coral, and then once you get north of 30 degrees, everything starts, because the coral is dead, so the coral can't keep producing more limestone. Everything falls prey to the erosion efforts by the ocean, and the whole thing starts to sink. Eruption on eruption, layer by layer, millennia after millennia over time. It's how these things were born. And I feel like I'm kind of beating the same horse, but I just want to make sure that this is sinking in, that what you were walking on is all formed by these volcanoes. There was nobody bringing truckloads of dirt over, millions of years ago and laying it in the middle of the ocean. This was all formed by volcanic activity. It's wild to think about, I think. Blows my mind. And like I said before, the older islands, the ones that are further away from that hotspot, they start showing evidence of the erosion a lot faster than the new islands do, because the wind, the rain, all the things that erode an island above the surface of the water is happening. And on Kauai, it's been happening for millions of years, much longer than on the other islands, because its island's significantly older. The shield volcanoes, nice gentle eruptions. That's why we're able to walk up to the Volcano National Park. It's why you were able to have that national park. If you went there, that visitor center is like 600 feet away from the edge of that crater. That's how we're able to do it. That was Mount St. Helens. There's no way you could stand right there. It may go off and take everyone out. There's no way. The shield volcanoes, they have this shape. They're not steep. They're big, they're round. This is why they make great islands. They have a peak, absolutely, but they make a lot of land mass because they spread slowly outwards instead of exploding upwards. Stratovolcanoes, which are the opposite, are things that you think about regularly, things you hear about, like Mount St. Helens, right? When it blew up, it blew up. You know, Pompeii, Vesuvius, these are stratovolcanoes. These are things that explode. Just the steam alone coming out of these things wipes out lots and lots of forest, people, whatever happens to be in the path of that explosion. Nothing can survive this. Now, down in Tonga, we have a new volcano that is exploding. This is actually a stratovolcano. It's not a shield volcano. When it first happened, nobody knew, nobody was there, nobody saw it happen really. When it first happened, we're like, what? We're getting a bunch of readings. We gotta go down there and check it out. Scientists rushed down there and yeah, explosions coming out of the water. And we've got it on maps. Cartographers get really excited about volcanoes in the ocean because they get to redraw all their maps. It's like guaranteed work. The only way we could really see it was from space, because that was the only way we were able to get a picture of the whole thing, what was happening there. So what's going to happen? What's going to be some of the first things that take over once that breaches the surface and calms down enough? Remember, wind, wings, wave, or man. That's how life gets moved to these volcanic islands. The coconuts, which float, they'll be one of the first things to colonize this island. Something else that occurs because of this, because this ash, this smoke, these particles that are kicked into the air impacts weather. A lot of these particles are charged. It impacts the atmosphere immediately adjacent to where this explosion is occurring. And certainly it impacts our lives. And we know that if a volcano is exploding, you cannot fly your airplane through that column of smoke. That column of ash will down your jet engine if you fly through it. So it alters not just the surface of the land, but everything around it. They're so powerful that way. These are just images I'm going to show you so you can sort of get an idea of the strength and magnitude of this explosion. I like this one a lot. Almost looks like some sort of nuclear device going off. Let's see the size of that aerosolized debris that's coming out of the volcano. Massive. But the ones that we were on, shield volcanoes, no big deal. You can go and stand there and take a picture of it because it's not going to explode. It's not going to blow you away. It's going to leak lava. You can go watch the lava, but you're not going to be blasted out of existence. Now, how many people went to see lava fields, either active lava field or lava field that had already cooled off? Yeah? Good. I'm glad you guys checked that out. So you know about these two types, and I know I mentioned this in one of the earlier talks, but I wanted to re-mention it for those who were absent. The pohoihoi is the really pillowy looking kind. Anybody see this when they were on your lava? Yeah, was it soft and pillowy looking? Like, was it comfortable? Could you lay on it? No, it would cut you to shreds, right? Even though it looks soft, it's still razor sharp. And then the other type, was when we talked about the a'a. That's the really rocky, gravelly type. These are the two types that exist in the Hawaiian Islands. Like everyone else, or like most people, I think the pohoihoi is very beautiful looking. I mean, makes you almost want to get close enough to touch it, which is insane because it's 2,000 degrees. Don't touch it. But you can see how they move. They move in this form that they take when they cool. They look pillowy. They look like a waterbed mattress to me when the pohoi is moving, and the looks like gravel when it's pouring down the street. It's beautiful. It's gorgeous. It's natural. This is something that is created by nature without man's assistance, and it is spectacular. So here you see both types of lava in the same exact spot. Pohoi on the bottom and on the top. How many people saw lava tubes? Yeah, this is really cool, right? This is a hollow point created during the movement of all of this lava. And this is, I will tell you, on my one of my bucket list things to do. Some of these exist underwater, and I am dying to go scuba diving through here. This is one of the things that, just like going skiing on the island, this is one of the other things that I would love to do someday. But the formation of it and its natural beauty is incredible. And I hope that you were able to travel through some. It sounds like some of you did. That's great. I know that a lot of them have been damaged recently due to seismic activity and due to some of the lava movement. I told you that the lava in Hawaii is the hottest lava on the planet. And keep in mind, let me back that up. Lava is magma that's on the surface. Because I know a lot of people sometimes wonder when it's lava, when it's not lava. When it's still in the earth, it's not lava. It has to come up, hit the surface, start rolling on the surface for us to call it lava. So that's the sort of the designation between the two. Hawaii's lava, hottest on the planet. Now, while it looks very calm and smooth, it can actually move at a decent speed. Pohoi can travel at 30 miles an hour when it's flowing. That is fast. If you're looking at these volcanoes, and after my lecture, going, if I get the chance to, and I come to a shield volcano, I'm just going to sit there and watch it because I can outrun lava. You cannot outrun some of this lava. And I can't imagine how terrifying that would be, just running and just having a 30 mile an hour flow of 2,000 degrees nipping at your heels. But don't do that. Don't touch it. Don't do that. The gases that come off of this can be very, very toxic. Now, steam, carbon dioxide, not a big deal, right? Hydrochloric acid, sulfur dioxide, hydrogen sulfide, however, not stuff you want to be breathing. And I know that this connects with the humidity that surrounds the Hawaiian Islands and creates this volcanic haze in the area. So I know that on the Big Island, there's people that move to the islands that have bad allergies or asthmatic conditions, and they're like, yeah, I'm gonna live in Hilo, and it's great, and I want to be on the Big Island, and it's nice. And then they're breathing in this stuff constantly because of the active volcanoes there, and it's horrific. That part of the island was actually socked in, and the eastern side and the southern side were socked in this haze for like a decade. And then only recently, as the activity level has sort of dropped, has that haze started blown away, and now the skies are more clear. But still, they can get this, and it impacts people's lungs. It's gnarly. This is the idea about lava-cooled steam explosions. Now, as this red-hot lava hits the ocean, 2,000 degrees meets 78 degrees. What do you think's gonna happen? You've probably seen people that work with metal, when they got red hot metal and they're hammering it and they put it into the water, and you've seen it go, like right as it goes in. This is that times, 80 million times, or more. Like it's very, very dramatic. There's a lot of energy, that red hot lava hitting that by comparison, cool water and exploding. It's very, very, it's actually very, very dangerous. And the government in Hawaii wants people to stay far away from it, which, is not our problem anymore. But if you were there at that time and there was something happening, you couldn't get anywhere near it. It would be very, very toxic and dangerous. these explosions, one of the other things that you may have noticed when you went to the national park, you'll notice these vents where steam is coming out, and they had signs that'll tell you, don't put your face in the steam. It's not, it's not a spa treatment. Don't do this. It's not good for your lungs. Because that stuff coming out of there is not meant to be breathed by human beings. But you see it and you're like, wow, that looks really cool, and you can get right up next to it. I don't know. People do interesting things. Something else that may not have occurred to you while you were there is that as this pressure builds up, now keep in mind, nothing is uniform that's happening there, right? It's all based on the movement of this energy from the hot spot. It's not evenly pushing across the underside of the crust. There are parts where it will sort of bulge. Pressure in one part of it may be higher than the pressure in another part of it. And we monitor this, and we hear about this, and if you go to the USGS website, they talk about this all the time. They talk about pressure, they talk about bulging. They talk about as this thing is building up, part of the land will actually rise up a little bit, noticeably, measurably. Part of the land, I mean, this is a very simplified instruction, but it would be like as if where I'm standing on this stage was pre-pressure buildup, the same level that you're on. And because of the pressure building, this part of the earth actually is bulging a little bit. It has a noticeable bulge, and we can measure this. We don't really notice it when we're walking around on it because you don't have a basis for comparison, because you can't make those sort of minute comparison details, but we do notice it. Scientists notice it, they measure it, and it's wild. So it'll bulge, but unevenly bulge, because the area where the crust is thinner, it's gonna be affected by the pressure more. That part bulges most. The earthquakes are also related to this. We know when we came around the corner there from Kona, and I made that announcement about the 130 thing, we know that one of the things the USGS was telling us is the amount of earthquakes have increased substantially as that volcanic area became more active. Now, this is a slide I had shown before about the flow. So about the lava flow that has occurred over time. Keep in mind, your volcano is over here, but out the sides here is where you've got lava flow. It's not coming out of this cauldron, it's coming out the sides and eking out towards the ocean. Why? Because the hot spot is over here. So this is a lot closer than this massive volcanic crater. The longest lived rift zone was at Pu'u'u'o'o. I know I'm not saying that well, but thankfully the Hawaiian interpreters aren't sitting in the back waiting to jump me afterwards now. This is the longest lived rift zone eruption of the last 2 centuries that we know of. The area that the magma covered and cooled in was more than 45 square miles. It added 230 acres of land to the coast. Now, it's one thing to say that it covered it because you're not adding new land per se, you're just covering up land that existed. The new land is where it reached out to where there was no land in the water and cooled, and now there is land. Someplace that you couldn't walk before because it was underwater, you can now walk onto. That's the interesting part about this as these volcanoes move. I'm gonna show you some pictures. You can see the change that occurred before and after. You can see the areas where this rift valley, this zone of lava flow, came out and extended out into the water. So here's a before shot, right? You can see this is the coastline. You can see there is movement of lava coming towards the coast. This is after. You can see all of this new land that did not exist before. This was not here. If you had beachfront property, you don't have beachfront property anymore. But it's magnificent to be able to watch. Now granted, this is not, if you didn't see this, don't worry, it's not happening right this second. You didn't miss anything. This is from that last time that the lava flowed out to the ocean. But this amount of new land, I'm repeating this so that you get an idea. This is how the Hawaiian Islands are born. This is how they continue to grow. They get bigger, or the active volcanic islands get bigger as new lava comes out towards the coast and expands the physical space those islands occupy in the middle of the ocean. And you can buy this. It's actually really, really inexpensive to buy a property there. I think it's called Volcano Zone 1. You cannot get homeowners insurance, not at all. So the people who lost their homes during this, who had homes in Volcano Zone 1, that's a total loss. And people will buy homes there. You go to these new lava fields, there are already people setting up small homes on it. You can't drill into it because there's nothing to drill in. It's just rock. There's no water underneath. So you have to bring in all your own water in, provide your own electricity, deal with your own sewage, and take all your garbage out, because none of those things exist. Obviously the city's not coming by to deliver your mail or pick up your trash. But it's actually relatively inexpensive. If that's something that you are interested in doing, hey, more power to you. Knock it out. You can live right there. The homes that are built are usually these sort of small home designs, and very, very clever with the way they're orchestrated in order to make maximum use of a small space. These volcanoes, like I mentioned before, they produce new earth, and that new earth is a place for new plants to grow, for new ecosystems to be born. This earth that's created from these volcanoes is very rich in nutrients, which is why plants start, even though it's hard as a rock, plants will start growing on it very, very quickly. It's a source of life, especially with the Hawaiians. They see it as a source of life rather than destruction. One of the first trees to move on it is the Ohalueha tree, and it signals the completion of one cycle and the beginning of a new one. It's one of the only forms of life that can grow directly out of the hardened black lava. Sort of needs, most of the other plants need a little bit of a pioneer species to come in and make it a little bit easier on them. But eventually, you get paradise. Eventually, you get a complete ecosystem on the Hawaiian Islands. Everything that you saw was formed in this manner. Everything that you were amazed by was formed in this manner. So today's lecture was just about to try to drive that home. And I hope that while it wasn't